In this video, we'll be looking at two different challenge problems from the Trimester 1 review. The first reads, when a sample of phosphorus burns in air, the compound P4O10 forms. Assume one experiment showed that 0.744 grams of phosphorus formed from 1.794 grams of P4O10. Use this information to determine the ratio of the atomic masses of phosphorus and oxygen. If the atomic mass of oxygen is assumed to be 16 AMU, calculate the atomic mass of phosphorus. We need to make a couple of assumptions before we can begin this problem. First, let's assume that P4O10 means that there's 4 moles of phosphorus to 10 moles of oxygen. Then we need to recognize that grams over grams per mole equal moles. That is, grams over molar mass will divide out to give us units of moles. Next, I want to look at P4O10 in a little bit more detail. P4O10 is really telling us that we have 4 moles of phosphorus to 10 moles of oxygen, which is another way of saying that the moles of phosphorus is equal to 4/10 the moles of oxygen. Now that we have those assumptions out of the way, we can begin with the problem. The problem tells us that 1.794 grams of P4O10 formed after 0.744 grams of phosphorus reacted. That means that 1.050 grams of oxygen must also have reacted. Now comes some algebra. Let's take the mass of phosphorus and put it over the molar mass. Remember, that will yield us moles. That's going to be equal to 4/10 the moles of oxygen, which is the mass of oxygen over the molar mass of oxygen. Again, moles of phosphorus equal 4/10 moles of oxygen. Now to simplify a little bit, we have 0.744 over molar mass of phosphorus equals 0.420 over molar mass of oxygen. Simplifying further gives us 0.744 times the molar mass of oxygen equals 0.420 times the molar mass of phosphorus. I cross-multiplied there. Isolating the molar mass of phosphorus, we find that it equals 1.77 times the molar mass of oxygen. That's the first part of what that question was looking for. And then the second part of the question says, let's assume that the molar mass of oxygen is 16, which it is. That gives us the molar mass of phosphorus being equal to 28.3 AMUs, which is relatively close to the accepted molar mass, so this could perhaps be a rare isotope of it. The second problem I'd like to look at deals with vitamin C. It reads, vitamin C, with a molar mass of 176.12 grams per mole, is a compound of carbon, hydrogen, and oxygen found in citrus fruits. When a 1 gram sample is placed in a combustion chamber and burned, the following data is obtained. And we're given the mass of carbon dioxide before and after the combustion, and the mass of an H2O absorber before and after the combustion. And then we're asked to find the molecular formula of vitamin C. Now what we can do here is use the mass of CO2 and the percent of carbon in CO2. We can use that to find the mass of carbon that reacted. And then we can take the mass of water and the percent of hydrogen in water and use that to find the mass of hydrogen that reacted. We know 1 gram reacted, so if we know the 1 gram minus carbon minus hydrogen, that gives us oxygen. So let's start with carbon dioxide. Carbon dioxide ended up at 85.35 grams and began at 83.85 grams, meaning that we gained 1.50 grams of CO2. Now, carbon is 12.01 grams over a total molar mass of 44.01 grams times 100 is 27.3% carbon. So we can take that 1.50 grams of CO2 and multiply it by 0.273 to get 0.409 grams of carbon. That's the amount of carbon that reacted when this vitamin C was combusted. Next, let's do the same thing with our water. The water absorber was 37.96 grams at the end and began as 37.55 grams, meaning that we gained a mass of 0.41 grams H2O. Hydrogen comprises 2.02 of the 18.02 grams, which gives us a percent of 11.2% hydrogen in water. Let's take our mass of water, 0.41 grams, multiply it by 11.2%, and we find that there are 0.46 grams of hydrogen that combusted in this 1 gram sample. We know again that 1 gram combusted. Of that, 0.409 grams were carbon and 0.046 grams were hydrogen, meaning that 0.545 grams were due to oxygen. Now we have our 3 masses of elements. We can treat this problem just like an empirical formula problem. As always, I'll take my masses and run 3 parallel operations. Convert each one of these to moles. And then divide by the smallest number, excuse me there, 0.034. And that will simplify my ratio. And then multiply by 3 to simplify it one more time. Here I have an empirical formula for citric acid. This has a molar mass of 88.07 grams per mole. We know that the molar mass of vitamin C is 176.12 grams per mole. We know that from the problem. So we can divide the known molecular mass by our empirical formula molar mass, find it's equal to 2, and then from there take 2, multiply it by our empirical formula, and get a molecular formula for vitamin C. Shown below is a molecule of vitamin C. Thanks for watching.